an example on capacitance and dielectrics, which was the topic that we finished last week. And then we're gonna finish today's chapter 16 by introducing capacitors in circuits, series and parallel, okay? So I wrote some of the equations that we went over last class, the equation for a capacitance and the equation or the relationship between the capacitance when you introduce the dielectric. So remember that the K value in this situation is the dielectric constant. It's not Coulomb's constant, okay? Now the two additional equations are this: the dielectric strength and the voltage when you introduce a capacitor. Sorry, the dielectric. When you introduce a dielectric, the electric field and the voltage, they are lower, right? They are reduced. We call the electric field when there's a dielectric, right? So when there's a dielectric, like in here, we say that there is a dielectric strength. And it's a vector as well. And we label it with capital D. That's the dielectric strength. It has the same units as electric field because it's just affected by the dielectric, by that equation there. In this example, they give you the dielectric constant. Again, no units. They give you the dielectric strength. You are given the capacitance. That's the capacitance you need. So this is the needed capacitance. And you have the voltage between the plates of 4 kilovolts. They want you to find the area between the plates. Okay, so if they tell you that that's the capacitance that you need, that means that that's the capacitance without dielectric. But the dielectric strength is this. So how do I use this to find the area? Well, even though you have a dielectric, the capacitance, this still holds. So you basically use this equation, right? The area is what you want. The distance you don't have. The capacitance is this. So, and E naught is a constant. You need to find the distance between the plates. You need to find this. To find the distance, you are going to use the voltage and the electric field. And you have the electric field because you have the electric strength. The electric strength, is the electric field divided by the electric constant. So I have that electric strength. I want the electric field, and I have this K. And that's how you find the electric field, by using that relationship. So let's see here. The electric field, if you do the math here, is 8.0 times 10 to the 8 volts per meter. So that's the electric field. If I have the electric field, I can use it to find the distance between the plates by using the electric potential relationship, right? Basically, for a capacitor, V equals to E T. Okay? So if I use that equation, right? The voltage is 4 kilovolts. That's 4,000 volts. Or 4 times 10 to the power of 3 volts. That's 8 times 10 to the 8 times the distance. Now, if I do the math here, distance is 0.5 times 10 to the negative 5, should be 0.50, right? Yes. Times 10 to the negative 5 meters. That's the distance between the plates. So I have the distance. Now I can use that to find the area because I have the capacitance. So 0.10 microfarads, which is that 0.10 10 to the negative 6 is E naught, and E naught is your constant, right? It is your 8.85 times 10 to the negative 12. That is your E naught. Area multiplied by area over the distance, which is 0.50 times 10 to the negative 5 meters. Okay, so well, let's see also the math here. Area equals to 0.10 times 10 to the negative 6 multiplied by 0.50 times 10 to the negative 5 divided by 8.85 times 10 to the negative 12. All of those powers of 10 will give me 10. 0.10 times 0.5 is 0.05. 0.05 divided by 8.85. .005,649 multiplied by 10, I get 0.056. So 0.056 meter square. And that's the area between the plates. Let's suppose they want it, so let's do the exercise. Convert to centimeters square. Convert to centimeters square. Let's suppose that you were being asked to do a conversion like that, right? If you were being asked to convert it, you have to multiply by 100 twice, basically by 10,000. So you move the 0, you move the dot, 1, 2, 3, 4. So that will give you 560 centimeters square. And that's another example where we use the capacitance equation and the dielectric. All right. Remember, I said last class that the dielectric changes the polarization of atoms inside a capacitor because you are introducing an insulating material, which allows you to increase the capacitance of the capacitor without producing a short circuit by reducing the distance too much. Okay. All right. Any questions about this? All right, so you already took quiz number 1 and assignments 1 through 4 or 5 are due next week. So you should be working on assignment 2 and 3 in preparations for Thursday quiz, right? So make sure you're working on that today after class. And right now I'm going to finish chapter 16 by introducing circuits with capacitors. So make sure that if something is not clear, then you can ask questions because we're gonna probably introduce current at the end of today, and tomorrow in person, we will introduce circuits with resistors, which is almost the last topic before the first exam, okay? All right, so let's erase the whiteboard right now, and let's go into circuits with capacitors, all right? Yeah, let's just do it on the whiteboard for now. Okay, so one of the last topics or applications, sorry, for capacitors is to use them in electronics. I did provide a brief explanation of how we do that last class. So now let's see what we mean when we talk about capacitors in series and in parallel. All right, so these will be capacitors in series and parallel. So for capacitors in series and in parallel, the idea will be to find a way to combine them into one and then use that combination to explore the charge, the capacitance, and so on. So what is the first step on this? When we have them in series, or for capacitors in series, normally the way they look is like this. You have a wire, capacitor here, more wire, capacitor here, more wire, capacitor here, and they are all connected to a power supply or a battery. So that's your very basic circuit. This is the voltage supplied by the battery, and this will be C1, C2, and C3. The way you can explore this is by understanding that when you have a circuit, and you're going to explore this tomorrow in the lab, is that in a circuit like this, we have current. Now, it doesn't make sense to talk about current if you have capacitors. So then we talk about charge, because capacitance is charge divided by voltage or potential. So technically, you have charge flowing through here. And because they are in series, all the charge is the same. So you write here that the charge on 1 equals to the charge on 2 equals to the charge on 3 equals to the total charge. So the total charge on the circuit is the same on each capacitor. So what happens with the voltage, however? By conservation of energy, the voltage on 1 plus the voltage on 2 plus the voltage on 3 is the overall voltage supply. So the voltage is split among each capacitor. Okay, but we have this equation, right? Voltage is Q divided by C. So for each capacitor, since they all have the same charge, V1 is Q over C1, V2 is Q over C2, V3 is Q over C3. And what's V? Q over C equivalent. We call that the equivalent capacitance. Well, all the charge is cancelled, and we get the equation to combine capacitors in series, which is basically 1 over C1 plus 1 over C2 plus 1 over C3. That's equal to 1 over C. And remember, Q is constant. Not voltage, but charge. That's capacitor in series. All right. Now, what about parallel? For parallel, the geometry is a bit different, but we're still going to use that equation. So for parallel capacitors, the way they look is like this. So let's write here parallel. And by the way, we still use the equation C equals to Q over delta V. Okay, capacitors in parallel look like this. Capacitor 1, capacitor 2, and capacitor 3. And they are all connected to a battery like that. That's your V, C1, C2, C3. What we notice is that these two ends, right? There is nothing in between here. So all of these capacitors are at the same potential, meaning that C1, C2, and C3, they all have the same potential or voltage as the one provided by the power supply or battery. So V1 equals to V2 equals to V free. You see that? And it's equal to V. The V of the power supply. Now, what's V though? V is Q over C. Now, the charge in this case is not constant. So you say Q1 over C1 plus, sorry. The charge is not constant, so Q1 plus Q2 plus Q3 is the overall charge of the circuit. Is the total charge. But what's Q1 though? Q is C times V. Now, C is different, but V is the same. So we can write C1 V1, C2 V2, C3 V3. That's your C equivalent times V. Now, because of this, V1, V2, V3, and V. And you get the equation for like this, but now for parallel, for parallel capacitors. So C1 plus C2 plus C3, that's equal to C equivalent. And these are the equations for series and parallel capacitors.
Professor, could you move the camera a little bit more to the right? Thank you.
Means the same. Now we're going to use those equations in circuits. All right. Now remember, this is for capacitors. If you have seen this with resistors, please keep in mind that they are similar but not the same. Tomorrow we're going to do resistors in series and parallel, and the equations are sort of reversed because of the conditions, right? A resistor is different than a capacitor. So please, when you are doing the problems, make sure that you know whether you are working with capacitors, which we're going to do now, and tomorrow when we start working with resistors. All right? Okay. So let's do some problems. And the idea behind circuits is a variety of circuits you can be given in a certain situation. Meaning, you have to figure it out whether capacitors are in series, in parallel, and which equation to be used. So let's do some exercises, all right? Yeah, start with one that is very common, and then we can move from there. Okay. Example on this. So one circuit you can be given may look like this. like that. Like that. Okay, so let's give some values now. 2 microfarads. So this is the capacitance of this is 2 microfarads or microfarads. 4 microfarads. 9 microfarads and 3 microfarads. Yep. And then the power supply, the voltage, let's say it's 6 volts. Negative, positive. So the typical questions that you can be asked are this. Find the equivalent capacitance. Find the total charge in the circuit. And the other question may be find the charge on each capacitor. All right. Okay. So the first step is to reduce the circuit so we can find the equivalent capacitance. So basically, reduce all those 4 capacitors into 1. Well, let's see. These capacitors here are in parallel. And also these 2 are in parallel. We join parallel capacitors by adding them. So your 9 and 3 basically combine into a 12 microfarad or faradio. And your 4 and 2 into 6. You have a 6 and a 12. And as you can see, they both are now in series. So to find the equivalent capacitance, we have to combine in series 6 and 12. Well, we use the equation for capacitors in series. One over C equivalent is equal to 1 over 6 plus 1 over 12. Right? Okay, so 1 over C equivalent is common denominator 2 over 12 plus 1 over 12. Now I can add this 3 over 12. But wait a second. That's 1 over C equivalent. So I flip it. C equivalent is 12 over 3, 4 microfarads or farads. That's my answer for A. Very easy. Now I can also find the charge. Here, the charge is the equivalent capacitance times the voltage supply. The total charge is the equivalent times the voltage supply, which is 6. So that will be 4 microfarads multiplied by 6 volts. All right. If you multiply a microfarad times 1 volt, the answer will give you, the answer will be microcoulombs. 4 times 6, 24 microcoulomb. And that's the answer for B. You see, very easy to find the equivalent capacitance and to find the charge on the circuit. Those two questions should actually be pretty straightforward. What you need to be careful though is how you find the charge on each capacitor. You basically have to go back, bring this back here, and split the charge, which you know in parallel is not constant. But let's go backwards though, all right? Let's do part C. For part C, you first need to notice, if you go backwards, that 6 and 12 are in series. So by the theory, you know that the charge on 6 is equal to the charge on 12 equals to 24 because they're in series. So you start with that statement. The charge on 6 is equal to the charge on 12, which is equal to 24 microcoulomb. So if that's the case, then you can use that to split the charge among 4 and 2 and 9 and 3. Let's start with 4 and 2. 4 and 2 are in parallel. Whenever you have capacitors in parallel, the voltage is the same. So like this, now you say that the voltage on 4 is equal to the voltage on 2. And what's the voltage on 4 and on 2? Is the voltage on 6. And what's the voltage on 6? Well, we need to remember our equation, right? So you may want to have this always. C equals to Q divided by V. Now, since I want voltage, voltage is equal to Q divided by C. So Q is 24 microcoulombs. And C is 6 microfarad. 24 divided by 6, 4 volts. So that means that the voltage on 4 is equal to 4 volts. By that equation here, the charge is equal to C times V. 4 times 4. Therefore, the charge on 4 is 16 microcoulombs. Similarly, the voltage on 2 is 4 volts. Then the charge on 2 is equal to 8 microcoulombs. How do I know that's correct? Because 16 plus 8 is 24 microcoulombs. All right. So I split the charge between among 4 and 2. All right. Now let's do 9 and 3. For 9 and 3, the analysis is the same. The voltage on 9 is equal to the voltage on 3 is equal to the voltage on 12. The voltage on 12 will be 24 divided by 12, which is 2 volts. How do I know that's correct? Because 2 plus 4 is 6. Conservation of energy. So we can just say here that the voltage on 9 is equal to the voltage on 3 is equal to 2 volts. If I have the voltage, just like I did here, the charge on 9 will be 9, the voltage, 2 times the capacitance 9 times 2, 18 microcoulombs. And by conservation of charge, 24 minus 18, 6 microcoulombs. Or you can just do 3 times 2. So the charge on 3 is 3 times 2, 6 microcoulombs. There you are. That's how you solve.
Wait, Professor, could you explain how you get 2 volt? Could you?
By dividing 24 by 12.
Oh, okay, got it.
All right. By dividing the total charge by the capacitance 12, which is the equivalent between 9 and 3, or the combination of 9 and 3. All right. Are there any questions about this or any other questions? So remember, that's just one example. There are different setups. I just did one of them. I'm going to do another one where we might have to do a different procedure, especially towards the end. All right. Keep in mind how I organize this, right? I try not to skip any of the steps. So all the steps are in there. And of course, the main difference between what you do in the web assign with what we do in class or even on quizzes is the numbers, right? I mean, I try to give you easy numbers, so look at those nice answers. Cengage, they give you very annoying numbers sometimes, but the procedure is the same. And I believe there is a problem like that in the assignment anyway. Well, let's do another one. All right. Let's do another one. All right. All right. So another type of setup that you can have also in circuits with resistors is like this. Two capacitors like this. Another one like this. Like that. All right, let's give some numbers now. 3 microfarads. Say 4 here. 12. 6. And 2. Get some fractions in there. And let's 12 volts. All right. So the first question for this again. Find the equivalent capacitance. Find the total charge. And now you're gonna find the charge on each, but also the voltage on each. I mean, you just saw over there that the voltage is that you can also split the voltage. So let's do that here. All right. All right. I'm doing this example because this is a good way to address a misconception that may happen in the assignment, on an exam, or a quiz. Be careful when you try and do this. And this. If you try to say that these are in parallel and these are in parallel, before realizing that these are in series, then you will get a wrong answer. And I've seen this a few times, it happens. So be careful. That's not correct. The main connection is first the series connection between 4 and 12 and between 6 and 2. So I'm going to combine in series these two. And then in series, I'm going to combine these two. Once you combine these two in series, you can then do the parallel connection between the combination of these two and these two. All right. So that's where you have to be careful. Once you realize that, then you are set to start this problem. 4 and 12, I'm going to write here 1 over C is in series, right? So we have to use that 1 over is equal to 1 over 4 plus 1 over 12. The common denominator is 12 times 3 times 3. 3 over 12 plus 1 over 12. That's 4 over 12. So 1 over C is 4 over 12. Therefore, C is equal to 3 microfarads. That's the combination of this. So let's write it here. That's the combination. All right. Now I'm going to do these two. 6 and 2. Let's call it 1.
Is the professor lagging for anybody?
Yeah, for me.
Yeah, bro.
Sorry, I think I had a connection issue. Let me see if the recording is still going on. Yeah. Okay. So what I was saying was the answer for part A will be combining 3 over 3.5. That will give you 4.5 microfarads. All right. That's part A. Now I can also do part B. Part B is asking me to find the charge on this circuit. Well, we have to write for part B, the charge is equal to C times V. So here will be 4.5 microfarads multiplied by the voltage 12. And that will give you around 54 microcoulomb. A and B. All right. So you found the charge on the circuit, Q total, and you found the equivalent capacitance, of course. All right. Now we have to do the charge on each and the voltage on each. The thing about splitting the charge and the voltage, you can basically do both at the same time. Let's see. So that charge is going to be split. Why? Because 3 and 3.5 are in parallel. You see? But let's take into advantage what we know about voltage. Since 3 and 3.5 are in parallel, then they have the same voltage. So let's forget about this for now. Let's focus on this. The voltage on 3 is 12 volts. So if I have the voltage on 3 and the capacitance, which is 3, I can find the charge on 3. And if I find the charge on 3, I know the charge on 12 and the charge on 4. The charge on 12 and the charge on 4 is the same. And the same to what? The same as 3. So I might have to write this in here so you have this as study or to review. First of all, the voltage on 3 is equal to the voltage on 1.5, which is 12 volts. And you may want to write there because they're in parallel. And then also the charge on 3 is equal to the charge on 4, which is equal to the charge on 12. All right. Now, from this first premise, if the voltage on 3 is 12, then the charge on 3 will be the capacitance 3 times the voltage 12. Well, 3 microfarads. 3 microfarads times 12, that's 36 microcoulombs. Perfect. That means I have the charge on 4 and the charge on 12. So I found the charge on 4 and 12. So you may want to go back to the diagram and write that the charge here is 36 microcoulombs. If the charge is 36, you can find the voltage on 4 and the voltage on 12. This is equal to 36 microcoulomb. Then the voltage on free is the charge divided by the capacitance. And what's that? 12 volts. Oh, wait. Something wrong here. Divided by 4. The voltage on 4. I already found 3, right? So why do I need that? This. So that's 9 volts. That's on 4. And what about 12? Well, think about it. Let's use some physics. The voltage is 12. 4 is already getting 9 volts. So the voltage on 12 is 12 minus 9, 3 volts. And there you are. I split the charge and I split the voltage. Sort of at the same time, you have to use both to kind of make sense of that question, right? Are there any questions? I want to do 6 and 2 now, but I want to make sure that that's clear. As I said, you want to write that the voltage on 3 and the voltage on 1.5 both are 12 volts because they are in parallel. And then you want to write that the charge on 3 is the same as the charge on 4 and the charge on 12 because they are in series. And then you can split the charge, and then using that you can split the voltage. All right.
Wait, so Professor, the 36 microcoulombs, is that for Q3 or Q4?
For both. They both have the same charge.
Okay, so Q3 equals Q4, which equals Q12, which equals 36 microcoulombs.
Yeah.
Okay, so it's really just a voltage that's not constant.
Yes, the voltage is split because in series that charge is constant.
Okay. Okay.
All right.
Wait, Professor, so Q3 and V3 is a combination of the top one, right?
Yeah.
Okay.
Yeah, we're just doing the top. We're going to do the 6 and 2 now. Okay, for the 6 and 2, you know what's the charge between 6 and 2. If the charge here is 36, and the overall charge is 54 there, right? Like the charge on the circuit is 54, and the charge here is 36. You know what the charge that is going through 6 and 2. By conservation of charge, 54 minus 36 is 18. That's the charge here. All right, so that's what you write. Let's write here Q is 18 microcoulombs. 54 minus 36. And then I just do the procedure. Let's erase this. So the charge on 6 is equal to the charge on 2, which is equal to the charge on 3 halves, which is 1.5. And what's that? 18 microcoulombs. So you basically split the charge already, if you think about it. You already found the Q on each. What about the voltage on 6? Well, the voltage on 6 will be the charge on 6, which is 18, divided by the capacitance. And what's that? 3 volts. Well, the voltage on 2, you can just say is equal to the voltage given minus 3 volts. And that's how you split the voltages. All right. Any questions? Nothing? So remember, we've done 2 different examples. I want to do one more just to reinforce we have time before we basically finish with this chapter. All right. The main idea or the main thing that you guys have to keep in mind is you just have to be organized. If you are organized and if you understand what series and parallel mean, then you are going to be more than fine. All right. And remember how we always keep using the equation C equals to Q divided by V, or its variances, right? Q equals to CV or V equals to Q over C. We use that equation. That's the key equation that we have to use to understand this. All right. It's built from that. All right. Let me just take a look and see what a good example of this. Wait. Yeah, this one. Okay, let's do another one. Okay. So one last example of this will be a circuit that looks like this. The battery here, a capacitor here, and then you have a junction sort of here. Why? Because you have a cable going here, and then another cable, wire, and then you have this connection. All right. 6, 3, and 2. Yeah, you know what? Let's give you something with fractions because might as well, so you know how to work with that. Yep, it's a good idea. And let's give you here 10 volts. The book won't give you nice numbers, so might as well give you one example like that. So let's find the equivalent capacitance. And let's find the charge on each. All right. In fact, you could see a problem like this in a final exam, maybe. Not the 2 questions, but maybe just finding the charge on one of them or find the equivalent capacitance. All right, so here maybe it's a bit easier to realize that 6 and 3 are in parallel first, right? Because of this junction. A junction or a node is an intersection of 3 or more wires. All right, that's going to be very important when we start doing more complicated circuits, especially with resistors. All right. So basically, if you think about it, you have charge slash current, and then it splits here and here, and then goes all the way here, and then all here, and then they combine again. Anyway, 6 and 3 are in parallel. So we combine these two. Into 9 microfarads. All right. But this one here and this one here, the combination of these two and this are in series. Therefore, we have to find the equivalent capacitance in series 1 over C cubed equals to 1 over 2 plus 1 over 9. Oh. Well, the common denominator is 18. So 9 over 18 plus 2 over 18, that gives you 18 over 11 microfarads. I mean, if you split, of course, because this is right. So you split it and you get that. Okay, so I found this. Now, how do I find that charge on each? Well, the problem is not asking you this, but we need to find that charge on the circuit. So I found the equivalent capacitance. Let's find the charge on the circuit. The charge is the equivalent times the voltage supplied there. And that will be 180 over 11 microcoulombs. Okay, let's approximate there. That should be around 15, 16. 16.4. There is approximately 16.4 microcoulombs. So that's my my charge. That's the charge on the circuit. Now, if we go back to this circuit, the charge is split here. But look, it's a split and then it's combined here. So I already know what's the charge on 2. The charge on 2 is the net charge of the circuit, which is 16.4. So the charge on 2 is 16.4 microcoulomb. Now I just need to split the charge between 6 and 3. All right. Okay. So the voltage on 6 is the same as the voltage on 3 because of parallel. And what's the combination of these two? 9, which is the voltage on 9. And the charge on 6 will be the voltage on 6 times the capacitance 6 microfarads. That's like Q. But what's the voltage on 6? What's the voltage on 9? Well, the voltage on 9 is the charge on 9, which is this, right? These two the voltage of 9. Like what the voltage of 9? The voltage of 9, yeah, will be the charge divided by the voltage of the combination. All right. Since these two are in series, the charge on 9 is this. Q divided by C. And that's approximately not 2, it's 1/2, I believe. 1.8. 1.8 volts. So that's the voltage on 9. Which is the voltage on 6? So what's the charge on 6? 1.8 volts multiplied by 6 microfarads. That will be 10.8 microfarads. All right. You can find the charge on 3 by using the same. The voltage on 3 is that. Six times 1.8 is, sorry, times 3. 1.8 times 3 is 5.4. 5.4 microcoulombs.
Wait, Professor, that doesn't add up to 16.4.
That's because of the approximation, because of this.
Okay.
That is approximately 16.36. I rounded to 16.4. And this actually gives you 1.8, 1.82. So that's why. So I'm rounding these numbers. But even when you add them, you get 16.2, so approximately. Right. Remember, these numbers are all because of this. That's an irrational number. All right. Or sorry, that's an infinite rational number, like has infinite decimals. So, but that's how you split the charge, the voltage, and the circuit given there. All right. So there you are. You should have, or you have now all you need to complete assignments